Hey everyone, welcome back to my YouTube channel Act 1. The anomaly, our solar system, a cosmic neighborhood we call home, extends far beyond the familiar orbits of Earth and Mars, past the gas giants Jupiter and Saturn, and even beyond the icy blue realm of Neptune. For decades, we thought Neptune marked the outermost frontier of our planetary domain, a lonely sentinel guarding the void. But as our instruments grew sharper and our gaze more ambitious, we began to uncover a vast, dark, and enigmatic region stretching billions of miles further. The Kuiper Belt. Imagine a cosmic donut, a colossal ring of icy bodies, remnants from the dawn of our solar system, orbiting the sun in serene, frozen silence. This is the Kuiper Belt, a treasure trove of dwarf planets like Pluto, countless comets, and a myriad of smaller, icy worlds, all locked in a slow, stately dance around our star. But as astronomers delved deeper into this frigid expanse, meticulously charting its inhabitants, they stumbled upon an anomaly, a profound mystery that challenges our very understanding of how our solar system formed and evolved. They discovered what has come to be known as the Kuiper Cliff. Instead of a gradual tapering off in the number of objects, a slow thinning of the cosmic crowd as one ventures further from the sun, there is a sudden, dramatic drop-off. It is as if the Kuiper Belt, so rich and populous up to a certain distance, simply ends, abruptly and without warning. The density of objects plummets, their numbers dwindling far more sharply than any known gravitational influence or observational limitation could easily explain. This is not a gentle slope, but a precipice, a sheer cliff face in the cosmic landscape. This abrupt boundary, typically observed around 50 astronomical units from the sun, is a profound puzzle. Why does the Kuiper Belt, a region theoretically capable of hosting countless more icy bodies, appear to terminate so suddenly? What force, what event, what hidden influence could have carved out such a distinct edge in the primordial disk of our solar system? It is a question that gnaws at the edges of our scientific understanding, hinting at unseen forces or undiscovered worlds, challenging the tidy models we have constructed of our cosmic origins. The Kuiper Cliff stands as a stark reminder that even in our own backyard, the universe holds secrets far more intricate and surprising than we can often imagine. It is a cosmic riddle, etched into the very fabric of our solar system's outer reaches, beckoning us to unravel its profound implications. The very existence of this cliff suggests that something extraordinary happened, or perhaps is still happening, in the distant, dark frontiers of our solar system. Act 2, the first clues the journey to understanding the Kuiper Cliff, begins with the discovery of the Kuiper Belt itself, a story that stretches back decades before our instruments could directly confirm its existence. The concept of a vast reservoir of icy bodies beyond Neptune was first theorized in the mid-20th century, notably by astronomer Kenneth Edgeworth in 1943 and independently by Gerard Kuiper in 1951. Edgeworth proposed a disk of small objects beyond Pluto, while Kuiper hypothesized a region of comets beyond Neptune, a leftover from the solar system's formation. Their predictions were remarkably prescient, laying the theoretical groundwork for what would become one of the most exciting frontiers in planetary science. For many years, Pluto, discovered in 1930, was considered an outlier, a peculiar planet in an otherwise empty region. But the theoretical seeds planted by Edgeworth and Kuiper suggested a much richer, more complex picture. The first direct evidence of this hypothesized belt arrived in 1992 with the discovery of 1992 QB1 by David Jewett and Jane Liu. This small, icy body, orbiting far beyond Neptune, was the harbinger of a new era of discovery. It confirmed that Pluto was not alone, but merely the largest known member of a vast population of similar objects. This breakthrough ignited a flurry of observations, as astronomers, armed with increasingly powerful telescopes, began to systematically survey the distant reaches of our solar system. The trickle of discoveries soon turned into a flood, and by the late 1990s and early 2000s, hundreds of Kuiper Belt objects, or KBOs, had been catalogued. These early surveys, while thrilling, also began to reveal the first hints of the Kuiper Cliff. As more and more KBOs were found and their orbits meticulously mapped, a curious pattern emerged. The distribution of these icy worlds was not uniform. Beyond approximately 50 astronomical units AU from the sun, the number of detected KBOs seemed to drop off sharply. It was not a gradual decrease, as one might expect from simple observational biases where more distant objects are harder to see. Instead, it was a precipitous decline, almost as if the Kuiper Belt simply ended at that particular distance. This observation was puzzling because current models of solar system formation predicted a much more extended, continuous distribution of material in this region. If the Kuiper Belt was truly a remnant of the primordial disk, why would it have such a distinct outer edge? Initial theories to explain this observed cliff were varied. Some scientists considered the possibility of observational bias, arguing that objects beyond 50 AU were simply too faint and too distant to be easily detected with the technology of the time. However, subsequent, more powerful surveys continued to show the same sharp drop-off, suggesting that the cliff was a real physical phenomenon, not just an artifact of our limited viewing capabilities. Other early ideas included the possibility of past stellar encounters, where a passing star might have gravitationally perturbed and scattered objects from the outer Kuiper belt. While plausible, such encounters would need to be precisely timed and oriented to create such a distinct, sharp boundary. The most compelling early theories began to center around the gravitational influence of unseen planetary bodies or the dynamic history of the